Okay, Andrea, do you want to kick us off?
Yeah. So, hi everyone. Welcome to the first DREAM seminar of this semester. This semester we're going to be virtual, as you can all tell. We're really excited to be hosting the DREAM seminar, and everything's going to be business as usual in terms of fantastic speakers and our usual 4 to 5 p.m. slot. But now what we're also going to be introducing and trying out this year is an open office hour style discussion with our speakers instead of having one-on-one meetings like we usually did. So for today's meeting, Kirill's going to be hanging out after his talk, starting at 5. So if people have any more pressing questions or want more one-on-one sort of Q&A with Kirill after the talk, please just stick around, stay on this Zoom call, and you'll have your questions answered. Otherwise, for other speakers that we'll have in the later parts of the semester, these office hours might happen at another time. So we try to make sure that the office hours happen usually on Mondays when the speaker is giving their talk, but sometime in Monday time frame that like really works for them. So just keep a lookout in all of the emails for when their office hours are going to be, so you can hopefully drop by and have some more one-on-one interaction with the speaker. But for right now, we're going to listen to Kirill and then host our office hours afterwards. Ken will take it away now with the intro.
Thank you, Andrea. And I want to thank you, by the way, for really taking the lead of organizing this series this year. And Andrea's been fantastic to work with. She's been working with a whole team of other students and faculty to put together a list of speakers, which we will post on the website and we'll be announcing every week. I also want to thank Samantha Tito for helping get the word out as well. And so this is sponsored by a number of faculty members as part of the DREAMS series and also the Citrus People and Robots Initiative. So we're delighted, as Andrea said, to kick off the current season. It's going to be unorthodox, but I think we're all figuring out new ways of doing things. And we have someone who's equally unorthodox to kick it off. And Kirill Solovey is from Israel. He did his undergraduate degree there at Tel Aviv University in computer science and went on to his PhD there, where he studied under Dan Halperin, the internationally renowned computational geometer and roboticist. And he has been extremely successful. Danny says wonderful things about him as being one of the most brilliant people he's ever met. And he says that he's won the Clory Scholarship, the Fulbright Postdoctoral Fellowship. He was a finalist at Robot Science and Systems, finalist for Best Paper Award. And then he actually won the Best Student Paper Award in 2015. He also got the Best Paper Award at the Multi-Robot Systems Conference. He was a finalist at the European Control Conference for Best Student Paper Award. And this year at ICRA 2020, he was finalist for Best Multi-Robot Systems Paper Award. And that's the work he's going to be talking about today. He is over at Stanford working with Marco Pavoni, and he's been doing a postdoc there and has been working on this area at this intersection of robotics, optimization, and transportation systems, and really thinking this through in terms of also how it will affect societal issues. So it's very timely. I'm super excited to welcome Kirill Solovey. Kirill?
Thank you so much, Ken, for the kind introduction. I'm very happy to be with you, and I'm thankful for the invitation to give a talk in your seminar. I didn't get a chance to visit Berkeley yet, but I hope that in the near future we'll be able to make those meetings personal rather than virtual. But this is the setting we have right now, and we will make the best out of it. So I'm very excited to present to you my most recent work on routing and task allocation for massive smart mobility systems. So in this talk today, we will explore applications of multi-robot systems in transportation science or in transportation systems as a mean to provide more efficient and more useful transportation systems and logistics methods for our society. And in particular, I would highlight 2 specific applications, one of which would be the use of multiple drones to perform package delivery, as well as the use of large fleets of autonomous vehicles to drive people around. So with that said, The talk will be focused on multi-robot systems, and we already have today multi-robot systems operating around us. So one of the most common examples for that is what happens when you click on the buy button when you're making your Amazon purchase. Every time you do that, you're actually forcing a whole fleet of those robots to carry shelves around the Amazon warehouses so that people who work in packaging those shelves and packaging items from the shelves would be able to send them to you. So the goal of those robots are to drive those shelves around in the warehouse. And there are a few more applications of multi-robot systems that we already have today. I'm hopeful that we will see more of them in the future. And I'm really hopeful that we'll see more applications of multi-robot systems that are used to really address important and big issues that we are facing today, such as the fires that we had in the last few weeks, where firefighting drones could really come in handy. And of course, we're not there yet, but we hope to get there one day. I am most excited about the prospects of the use of multi-robot systems in smart mobility and in transportation. So at least in my area, and I'm sure that in Berkeley, you already see those autonomous vehicles driving around as well. We have them, we see them on a daily basis. But it won't be long before we'll have entire systems of those autonomous vehicles embedded into our city's infrastructure. Now, the important thing to understand when we're talking about multi-robot systems as a whole, and in particular about smart mobility systems, that if we want to really reap all the benefits that are associated with them, namely safety, efficiency, and addressing societal issues such as congestion and fairness, then in order to get all those rewards, we must understand how to control those systems, not from the perspective of the individual agents that comprise them, but from the global perspective, by accounting for the interactions of all those agents together and how they influence one another and the environment in which they operate. Unfortunately, controlling smart mobility systems is tremendously challenging, and there are a lot of technological reasons for that. And here I want to highlight the computational aspects of those issues. From the most general perspective, in order to control effectively multi-robot systems, we need to account for the interactions between the different agents. And this in itself introduces a very high dimensional search space, which is very difficult to reason about. If we're moving to the setting of smart mobility, then this only gets worse, because we have many agents that need to operate on a city scale area. We have many passengers that are willing to travel in a given city, for example, which we need to also consider in our modeling approaches. And the last ingredient is that when we're talking about smart mobility systems, is that in order to really make those systems efficient, we must understand how they impact the environment and how the environment impacts itself. So in order to do that, we must account for complex mathematical models for instance, traffic flow as well as human behavior in order to make them really efficient. Now, with all of those challenges, one thing that we also need to be able to provide is strong guarantees on the performance of our control mechanism in terms of the quality of the solution, its robustness, and running times, for instance. So all of those considerations make the design of fast and efficient controllers for multi-robot systems in particular and smart mobility systems in general very challenging. So what I'm doing in my work, I work in the intersection of robotics, optimization, and transportation sciences in order to address those issues with the end goal of making robotic systems more useful to us and beneficial for the society. As a PhD student in Tel Aviv University, I started working on multi-robot systems on one of the most fundamental problems that you can think about in this setting, which is simply finding routes that avoid collisions for the individual robots while moving them from their origin, from some start positions to their goal positions. And this problem is called multi-robot motion planning. And already on this basic level, the problem is tremendously challenging to account for. There are many heuristics that try to solve those problems in practice. In one of my first papers ever, together with my collaborators, I observed that there is an interesting connection between those continuous problems for multi-robot systems in the real world and different tile sliding puzzles, such as you can see on the right. And I'm sure that you got a chance to play with those puzzles on your own. So by exploiting this connection, what my work has shown that we can decompose those complex multi-robot problems into a sequence of puzzle-like problems that can be solved very efficiently. And this eventually led to the development of some of the most scalable algorithms for multi-robot motion planning. However, all of those approaches that I mentioned on this slide are currently limited to a relatively simple robotic systems that have holonomic constraints, for instance, and are bounded to work in the plane. So to overcome these challenges and to provide more general tools that can work for different types of robotic systems, I realized that I need to study more closely sampling-based approaches for motion planning that were initially designed for single robot systems. So what's important to note about and understand about sampling-based algorithms for motion planning for an individual robot is that they avoid reasoning directly about the high dimensional search space of the problem by instead sampling this space, where each such sample simply represents a different configuration for the robot. And due to this fact, it's very easy to implement those algorithms on various robotic systems, which allows them to be implemented in practice quite efficiently. And in this domain, together with my collaborators, we designed a few novel algorithms, but we also helped to uncover and to resolve several big misconceptions in this area of research. And in particular, for example, we only recently provided the first ever proof for why algorithms like RRTs and RRT stars actually work in practice. So leveraging this understanding of how we can design sampling-based algorithms for single robots, we turn to extend those techniques for multi-robot systems. And the main observation that we got in this domain is that we can leverage independent sampling-based roadmaps that were developed or constructed for individual robots in a manner that allows us to solve multi-robot problems efficiently while also guaranteeing strong theoretical guarantees, such as that the quality of the solution that we return would be optimal. Okay, one last component that usually appears in most multi-robot systems is task allocation. So if we could take, for example, this setting of Amazon warehouse, the main question before we actually find paths for our robots is how do we decide which robot takes what shelf? And this is the task that task allocation mechanisms need to solve. And we will see along the way as we move to the setting of smart mobility that this problem also emerges again and again. So for the remainder of the talk, I will focus on the applications of multi-robot systems in smart mobility. And of course, here we will move to a much larger scale. So for the first part of the talk, I will consider the use of multiple drones to to make package deliveries over a large urban area. And the second would be concerned with routing of autonomous vehicles in a city. Now, along the way, I will highlight both algorithmic aspects as well as the broader implications of those algorithms and the interaction with the society. So the motivation for the first work comes from the fact that we all love using online shopping. I'm sure that some of you in the crowd have already ordered something today. And if it wasn't some tool from Amazon, it probably is some package for some food item from one of your favorite restaurants. And especially in this time of COVID, online shopping has become very useful for us because we can avoid going outside. But even in more peaceful times, it has one big disadvantage, namely that in addition to others, which is that it introduces very high loads on our road networks through the use of package delivery trucks. So just as a curiosity, I can mention that trucks, which consist of only a small portion of the road traffic, introduced to as much as 28% of the nation's congestions. And the situation is even worse if you think about new services for package delivery, such as Uber Eats, and DoorDash, which are even more inefficient than that. In parallel, both researchers and companies have started to consider the use of drones for package delivery services. And the benefits of that are obvious. We just can avoid using our road networks and instead fly in the air. And this can make those services much more efficient. However, there is a big issue that we need to overcome, which is that in most drone systems, their flight range is very limited. And this is even more severe when we consider that they also need to carry some heavy package. So this is what our most recent work tries to overcome. And this paper was recently introduced in ICRA. This is joint work with Shushman Chowdhury, who is a PhD student here in Stanford, as well as Michael Kochendorfer and Marco Pavone. So the goal of our work is to design a service for package delivery using a fleet of many drones. We are given a collection of packages to deliver over a large urban area, and we need to specify allocation between drones and packages, as well as the routes that the drones would take, in order to speed up or to minimize the delivery time of packages. A distinguishing feature of our framework is that we allow drones to land on top of public transit vehicles and essentially hitchhike on top of either buses or trains in order to conserve their energy, and by that reduce the delivery time. So just as an example from our experiments, which we, from simulations that we performed over the city of San Francisco as well as Washington, DC, we see that using such a framework or an approach where drones rely on public transit networks, we can increase the effective service range of drones by as much as 4, which is quite a lot. So just to give you an example how it would look like, just at least in the simulation, here we can see a simulation of such an approach applied to the real transit network of San Francisco. The circles here represent drones. The blue points are drones that are currently in flight mode, and the reds are, for example, the one that you can see now on the screen is a drone that is currently hitchhiking on a bus. So just finish. Okay, so we not only came up with the framework, but we also designed an an effective algorithmic framework to tackle this problem. And the problem consists of many components, both the large transit network, many packages that we need to distribute, and also interactions and conflicts between the different agents that we want to avoid. We want to avoid collisions between agents. We want to avoid too many agents to land on top of the same public transit vehicle at the same time. So all those considerations introduce very complex optimization problems, which seems to be very tricky to solve in one shot. So what we do in the paper, we present a scalable approach that breaks the problem into two steps. On the first level, we perform a task allocation, which finds the assignment between packages to drones and the order in which those packages would be distributed. Now, while doing so, we are using some approximation or representation of the public transit network, but we ignore on the first level the interactions between the different agents. What the second layer does is it employs techniques for multi-agent pathfinding in order to execute the allocation in a manner that minimizes the execution time, but also avoids the conflicts, different conflicts and collisions between the different robots. Now, of course, this work opens a lot of questions that we need to account for and resolve before we actually implement such an approach in the real world. For instance, how do we allow drones to safely fly in densely populated urban areas? And how do we allow drones to land on moving buses? All of these issues. There are a lot of issues, and I'm sure that you can think about other challenges that we need to address. Having said that, we were recently contacted by an operator of one of the largest mass transit operators in the US, and they were actually crazy enough to consider implementing the service in their city. And we're currently working on a case study in which we're going to assess the economic viability of using such a service in the real world. I think that it's a good time to see if you have any questions about what we have seen so far in the talk. So I'll give you a couple of seconds or a minute to respond if you want.
Actually, Carol, I'm actually just curious about the idea of the piggybacking on the buses or the trucks that you're talking about here.
Yes, Ken.
So it looks like that's actually, you have a UPS sign on it. Is this actually something that's being explored?
Yeah, so this is something that also is being explored both by industry, as you can see, as you noted from this figure. It's definitely studied in the scientific literature, although most of the work right now considers the use of a single drone with a single truck. And we're also considering to extend our approach, which would also account for the use of a truck in order to provide coverage in areas of the city that are not well serviced by public transit networks. So
Good.
It's definitely something that has been considered, yeah.
Good, okay, good, thanks.
Thank you for the question.
I have a quick question. So in the prior slide to this, you were talking about how you break up the problem into first assigning which sort of tasks, the task allocation problem and then the planning problem. Yeah. So it seems like intuitively to me, it's really hard to separate the two. Like it's hard to know which task to allocate unless I do like a planning problem of sorts and then determine based on some like cost of that planning under that task allocation, one task might be more or less desirable. So can you talk a little bit more about this decoupling and sort of what implications that has?
That's a really good point, and it's definitely the Achilles heel of this algorithmic approach, where we are decomposing the problem into two different steps where the higher level is essentially oblivious to the interactions between the different agents. So one way that we're trying to account for that in the top layer is by using some version of a surrogate function, which tells us what would be the estimates of the actual execution of the approach when we involve the agent themselves. But I definitely agree with you that there is a lot of things that we need to do here. We need to study this problem more deeply. I would say that it's still very challenging, and this is a similar approach is also used currently by, at least from the academic perspective, in papers that address task allocation issues in Amazon warehouse. So it's definitely a problem, an issue that arises in many different applications. And it seems at this point too challenging to combine it together into one solution.
Yeah, I'm curious if there's like small instantiations of the problem where maybe the number of agents is relatively small as is the number of tasks, where you could actually know what the optimal task allocation is if you knew all the optimal plans, and then figure out how much are you losing when you do decoupling. Because I feel like, you know, like especially when we deal with a lot of robotics problems, decoupling, like making things simpler or adding heuristics or decoupling the problem is often like really desirable, but maybe doesn't actually decrease the performance that much. So I'd be really curious to see that comparison if there exists an optimal sort of benchmark. But I understand, like, you know, in these examples you're showing, they're really, really complex. So makes sense.
Yeah, I would say that even in small examples where for a small warehouse where you have just a few robots, it blows up very, very quickly. But with that said, it's definitely possible that maybe we will find some structure that we can leverage in those cases. Yeah. Thanks for the great question. So I suppose that we can move on to the second part of it.
There's one quick question in the chat. I don't know if you can see it easily from your view.
Yeah,
I can also read it aloud if you'd like.
If you can do that, that would be great.
So David McPherson asks, for piggybacking on public transit, what cooperation would you need from the transit authorities? Would they need to add mounting hardware?
It definitely seems that like we will need some specialized hardware to do that. Yes, yes. I would say that there are a few works in the literature that consider the landing of UAV on top of a vehicle, but it's not clear whether it's applicable to, whether it's robust enough and small enough to be used on a bus, for example. Yeah. But this is definitely one of the things that we need to establish together with the transit authority. Another thing that maybe it's worth mentioning here is that perhaps we can even allow drones to charge while they're sitting on top of those buses. This would be a nice way to charge them while they're not being idle, actually. Yeah.
David says thanks.
Okay, so with that, we can move to the next part of the talk. And our goal here is to understand the problem of autonomous mobility on demand routing. So what is autonomous mobility on demand routing? This is very similar to what we currently have with Uber and Lyft, ride-hailing services, where you can just order the service online or from an app. And the difference is that we're operating from a centralized perspective, a fleet that is entirely autonomous. And because this fleet is entirely autonomous, then we can strive to achieve better performance than traditional ride-hailing services. But with that said, I would like to mention that some of the ideas that we bring from this area can even be applied today to ride-hailing services. Now, the important thing to understand when we're thinking about AMOD systems is that in the future, they would be huge. We will have many of those autonomous vehicles driving around. And we can no longer ignore the effect that the individual vehicles have in the system on each other in terms of the travel times. So the system is so huge that it would introduce in itself congestions and increase travel times for different vehicles. And we need to account for this and design controllers that are congestion aware. There is quite a lot of work in the area of AMOD routing, autonomous mobility on demand routing. There are a number of approaches that capture and model the problem from a queuing theoretic perspective, as well as different ways to implement the solution in practice. There are even approaches that combine the use of AMOD systems together with the power grid, public transit, and ride sharing. However, most of the approaches that I just mentioned are congestion unaware. That is, they assume that travel times in the system do not change no matter how many vehicles we send, for instance, through a single road segment. There is a small number of techniques that are congestion aware. However, they are not scalable enough for our application because they usually rely on the use of some version of a mathematical programming of the problem, which is very highly non-scalable. In our work, and this is joint work with Mauro Salazar and Marco Pavone, we show that we can exploit the specific structure of the AMOD routing problem in the design of an algorithm that is fast, congestion aware, and it has strong theoretical guarantees. So from the theoretical perspective, we show that our approach is guaranteed to minimize the total travel time of all the vehicles in the system while accounting for congestion effects. From the practical side, we show in simulations that we can solve massive problem sets within a few seconds. For example, we can tackle the entire rush hour traffic of Manhattan just in a few seconds on a commodity laptop. And in fact, the approach is even faster than congestion unaware approaches. That is, we are not only faster than those approaches, we are also more accurate in the way that we model congestions.
I have a quick question.
Yeah, sure.
So what about the problem structure allows you to do it so well?
So we will go into the details in the next few slides. Yeah, so before we dive into the details of the algorithm, let me briefly describe how does the problem that we're trying to solve looks like. Mm-hmm. So obviously we have some sort of a graph that represents the road network in our case, where every edge of the graph represents a different road segment in our city. In addition to the topology of the city, we also have some characterization of the demand, namely how many people are interested in traveling between every pair of origins and destinations. So just in this example, we know that this person wants to go from here to here and so on. And our goal is to specify routes for our vehicles to satisfy the demand, but also to minimize the total travel time introduced by all the vehicles in the system. Now, when we are planning routes for our vehicles, we need to specify routes of two types. The first type is routes that take a passenger from its origins to its destination. The second, so at least in this example, the demand is constructed in a way that we will have vehicles that are accumulating in certain vertices of the graph. So all of those vertices are destination vertices for our vehicles. So unless we do something about it, we'll have vehicles that won't drive to other places in the city. So we also need to ensure the rebalancing of our system. And to do that, we need to not only specify routes for those empty vehicles, but also assign them to locations or passenger locations. So we essentially have both task allocation and routing combined together into this second problem. So another ingredient that we have in order to be congestion aware, at least to a certain extent, we assign to every edge in this graph attributes that characterize the performance of the service, that characterize the performance or the travel time along the edge as a function of the number of vehicles that go through the edge. So let me give you a little bit more details about that. So what we assign to every edge is a so-called volume delay function. And this is a very simple concept. Volume delay function is simply a function of the traffic flow over the edge, that is the number of vehicles, and it returns the travel time along the edge. So if we have very low traffic volume, of course, the travel time is very low. And as we increase it to a rush hour setting, then the travel time increases as well. So we have such a function that is assigned to every edge in our graph. And combining all those ingredients together, the problem induces a convex program. The goal function in this convex program corresponds to minimizing the total travel time of all the vehicles in the system. So in particular, the goal functions looks like that. We are summing over all the edges in the graph, where for every edge, we compute what would be the travel time of all the vehicles driving along the edge. And this is simply the number of vehicles driving along the edge times the travel time, which in itself is a function of the number of vehicles along the edge. So this is the volume delay function that we have here. Of course, in addition to the goal function, we also have constraints in order to make sure that we satisfy the demand and we rebalance the system. And our goal is to find an assignment X, which specifies routes for the vehicles in the system while minimizing this goal function. So the fact that the problem is convex is of course useful mathematically, but this in itself is not enough. Because if we just take out of the box convex programming approach and run it on this optimization problem, we will get running times on the order of several hours, which is unacceptable. So the main insight that we obtain in our work is that we can transform our AMOD routing problem into a simpler problem called traffic assignment. So what's important about traffic assignment is that in this specific case of the problem, we have every empty vehicle has a specific goal destination, unlike the AMOD setting where the allocation needed to be specified by our optimization approach. So how do we make this transformation? So if we consider this example, we know that we will have empty rebalancers accumulating in those vertices. We can slightly modify the structure of this road network and the demand to ensure to specify a global destination for all the rebalancers in the system. In particular, we add a virtual vertex and a few virtual edges that connect between the origins of passengers to this virtual destination node. So in this new problem, all we need to do is to find the routes that for all the passengers from their origins to the destinations, as well as for all the vehicles, empty vehicles from their origins or destinations as well. So it seems like the difference between this problem and the original problem that we had is quite minor, but in fact, it's very powerful. So first of all, from the mathematical perspective, what we show is that if we carefully assign the properties of those new virtual edges, then the solution that we obtain from this new traffic assignment problem will yield an optimal solution from the AMOD routing problem, which also includes rebalancing. So this is great, but still this is not enough because we still end up with a convex program that captures the traffic assignment problem. Now, in order to really solve our original problem quickly, what we do is we combine approaches that are old and new. So the old approach that we're using is one of the most standard convex optimization methods that are known. And we're just basically applying a gradient descent approach. But here there's some magic that happens when we apply a gradient descent approach for specifically on the traffic assignment problem. And this is a property that has been known for a while in the transportation community. In particular, this property goes as follows. So if we consider a standard application of a gradient descent approach over a general convex optimization problem, then in every step of the algorithm, it would solve some linear version of the problem, which is typically solved using linear programming. What's unique in our case is that this linear version of the problem is equivalent to solving multiple shortest query problems. And this is quite mind-blowing, for me at least it was, because it's such a simple property, but it's so powerful. So instead of solving linear programs in every linearization step, we can quickly solve shortest path queries. The last piece of the puzzle here is that is a recent work by a group from Karlsruhe that allows to solve those shortest path queries specifically from transportation networks very efficiently. And so combining all those ideas together, we get a very efficient approach that is congestion aware and has strong theoretical guarantees on the quality of the solution. And we're currently considering several extensions to make the approach more accurate in practice. For instance, one of the main simplifying assumptions that we make in the model that I just showed you earlier is that we assume that the travel demand is time invariant. That is, the demand does not change between one time segment to another. And this can be applicable to certain times of the day, but it's not true globally. So we're currently designing an extension of the approach that would use more advanced models for traffic flow theory in order to capture more accurately traffic flow and also be extended to the time varying setting of the demand. Another important ingredient that we're currently aiming to capture is the fact that demand is usually not fixed, which we assumed earlier, but just from economics, we know that demand depends on the quality of the service that we provide. So we're currently considering an extension where we employ elastic demand models, which are simply functions that tell us what would be the demand or the number of people who are interested in traveling as a function of the quality of the service that we provide. This introduces a very complex optimization problem because we need to simultaneously solve our optimization together with simultaneously routing our vehicles, which in itself changes the travel demand, where the travel demand changes the routing scheme. In the future, we're planning to consider several extensions which would allow to provide more effective transportation services. With that, we must understand that there is a limit of how much efficiency we can get just from relying on single occupancy vehicles. The thing is that the private vehicles that we have today, as well as autonomous vehicles that we will have in the future, would still be very inefficient in terms of their space use if we compare them to traditional mass transit services like buses or trains. So in the future, it would definitely be important to understand how to operate an entire system that consists both of AMOD as well as buses and trains. Now, this leads me to my last point, which is until now, we ignored some very important component of our transportation systems. Our goal is beyond introducing cool technological advances and autonomous vehicles and so on, is to provide more effective transportation, which can also address societal issues that are currently present in our world. So we already mentioned congestion, and another important aspect would be to account for the environmental impact of those systems. But another important ingredient is how does those systems influence the society in a way that ensures equality or doesn't introduce bias. On the flip side, if we're not careful when we are designing those algorithms and systems, we can introduce just more bias. And just as an example for that, from recent years, it has been shown recently that dynamic pricing algorithms that are used by Uber and Lyft, at least in the city of Chicago, increase prices in lower income areas, which is incredibly unfair. And in that context, I would like to mention an ongoing project that we have here in Stanford, where we are developing a framework to address wheelchair accessibility in traditional ride-hailing services. And our goal is to provide regulatory tools for policymakers, as well as operators of ride-hailing services, in order to understand what would be the right decomposition of their fleets in terms of the number of wheelchair accessible vehicles as well as standard vehicles to ensure a fair service to all the users in the system. So of course, from a more broad level, in the future, we need to team up as engineers, algorithm designers, and roboticists with both researchers from social sciences, as well as policymakers and stakeholders, in order to really understand and address societal issues that are currently happening in our transportation systems. So with that, I would like to conclude this talk. We presented the 2 applications for multi-robots in both package delivery as well as autonomous on-demand routing. And along the way, we highlighted both the algorithmic ingredients of those problems, as well as the broader implications of the systems. With that, I would like to thank the audience for your attention, as well as all my collaborators that I mentioned throughout this talk. Thank you for your attention.
Thank you, Kirill. Terrific. Thank you on behalf of all of us. It's great talk, and I'm sorry I'm going to have to leave in just a few minutes, but I do have 2 quick questions I want to ask you about. One is just a little bit of insight into how you would address this fairness question. In other words, it seems that adaptive pricing is going to look at supply and demand, and how can you actually counter that and to make it fair? And because it seems to be almost anything that's going to do that actually could be inherently unfair. There may actually be a proof that there is no such thing as a fair adaptive pricing system. And then the other is the reduction you showed about to those shortest path problems. If you could just give a little more insight into what is going on there, that would be appreciated.
Okay. So about the first question, you're raising a broader question of what is equality, what is equity, and how do we define it, how do we characterize it? And it is true that you mentioned also the pricing mechanisms that may be helpful or may even introduce inequality. So for instance, one way that we can improve pricing mechanism is to incorporate into them not only different characteristics like what is the time of the day or where I'm traveling from, but who is the person who is traveling. Maybe it's a mother that has 4 kids, and maybe it's a wealthy well, maybe it will be me in the future, but I don't know. Maybe it's some tech company owner, or so. These are definitely tricky questions, and I don't have a good answer for that for now. But and this is why I'm also looking forward to team up with people who study those issues of equity, social sciences, to understand their perspective. About the second component that you mentioned, this routing, the fact that it breaks into shortest path queries, this is actually not a very tricky thing mathematically to understand here. It's just that if you will take the traffic assignment problem and you will write down the linearization of the problem, what would be the goal function in this case, then the interpretation would be that you just need to solve independent shortest path queries. So it just all follows from the mathematical structure of the traffic assignment problem that we're solving here.
Very good, thank you. Okay, Kirill, I've got to take off, but I think others are here. We have about 20 people there, and so there's a few questions in the chat, which are you could answer there. And thank you again from all of us for the talk, and we'll hope to see you again soon.
Thank you so much. It was a lot of fun, and I'm looking forward to discuss those questions further in the next hour. So.